Event sourcing is a powerful architectural pattern that changes how data is stored and managed in complex systems. Instead of saving only the current state of data, it records every action or event that happens to an object in an append-only store. This means you have a complete history of changes, not just the latest snapshot. The event store becomes the system of record, enabling you to reconstruct the current state of any entity by replaying its events. This approach brings significant benefits in terms of performance, scalability, and auditability, especially for high-load applications where traditional data management falls short. Most applications use the CRUD model, create, read, update, delete, to manage data. This approach is simple and effective for many scenarios, but it has its drawbacks. As systems scale, performance can degrade due to resource contention and locking. CRUD systems are synchronous, so updates can block other operations, leading to bottlenecks and higher latency. Additionally, CRUD only stores the latest state, so unless you implement a separate audit log, you lose the history of changes. These limitations become more pronounced as your application grows or requires higher reliability and traceability. With event sourcing, every change to an object is captured as an event. These events are recorded in an append-only event store. Application code raises events that describe what happened, such as item added to order or order canceled. These events are sent to queue where event handlers listen and persist them. The event store acts as the authoritative source of truth. At any time, you can replay all events for an entity to reconstruct its current state. This decouples the code that generates events from the systems that consume them, allowing for greater flexibility and scalability. Playing all events to get the current state can be expensive, especially as the number of events grows. To address this, applications often use materialized views, read-only projections of the event store optimized for querying. For example, a system might maintain a materialized view of all customer orders to quickly populate the user interface. As new events occur, handlers update these views, ensuring that queries remain fast and efficient. This approach balances the benefits of event sourcing with the need for responsive applications. Typical workflow in event sourcing starts with the presentation layer, which reads data from a read-only store to display in the UI. When an action occurs, like adding an item to cart, the command handler retrieves historical events for that entity and replays them to materialize its current state. Business logic runs and new events are raised and pushed to queue. Event handlers then write these events to the event store, update materialized views, or integrate with external systems. This workflow ensures that every change is tracked and can be replayed or audited at any time. Event sourcing offers several compelling advantages. Events are immutable and stored using append-only operations, which improves performance and scalability by eliminating data contention. The decoupling of event producers and consumers allows tasks to run in the background, enhancing responsiveness. Events are simple, domain-relevant objects, making the system easier to understand and manage. The append-only nature also provides a complete audit trail, enabling you to regenerate state, analyze trends, and debug issues. Additionally, event sourcing helps prevent concurrent update conflicts and supports flexible integration with other systems. Event sourcing is often combined with the command and query responsibility segregation (CQRS) pattern. In this setup, the write store is based on event sourcing, capturing every change as an event. The read side uses materialized views for efficient querying. This separation allows you to optimize each side independently. Writes are fast and conflict-free, while reads are tailored for performance. CQRS and event sourcing together enable systems to scale efficiently and adapt to changing requirements, especially in domains with complex business logic. One key consideration with event sourcing is eventual consistency. When events are added to the event store, there's a delay before all consumers process them and update their views. This means the system is not always immediately consistent. There's a window where the latest changes might not be reflected everywhere. Applications must be designed to handle this, and users should be comfortable with the idea that data may be slightly out of date for a short period. This trade-off is often acceptable in exchange for the scalability and flexibility event sourcing provides. Managing event versions and maintaining the correct order of events are critical in event sourcing. Since the event store is the permanent record, events should never be updated. Only new compensating events can reverse changes. If the schema of events changes, you must support multiple versions, which can be challenging to maintain. Additionally, ensuring that events affecting the same entity are stored and processed in the correct order is vital, as the sequence determines the entity's state. Techniques like timestamps and incremental identifiers help maintain order and consistency. Like traditional databases, querying and event sourcing isn't as straightforward. There's no SQL-like mechanism for extracting information directly. To determine the current state of an entity, you must replay all related events from the event store. For entities with long event streams, this can be costly. To optimize, systems often create snapshots at intervals, storing the entity's state at a point in time. When reconstructing state, you start from the latest snapshot and replay only the events that occurred after it, balancing performance with accuracy. While event sourcing reduces the risk of conflicting updates, inconsistencies can still arise, especially due to eventual consistency and lack of transactions. For example, a stock reduction event might arrive while an order is being placed, requiring reconciliation. Event consumers must also be idempotent, meaning they can handle the same event more than once without causing errors. This ensures that even if an event is processed multiple times, the system's state remains correct. Designing for idempotency and conflict resolution is essential for robust event source systems. Event sourcing is ideal when you need to capture the intent and history of changes, minimize conflicting updates, or maintain a detailed audit log. It's especially useful in systems where you want to replay events to restore state, roll back changes, or analyze user behavior. If your application naturally works with events or needs to decouple input from processing, event sourcing can provide significant benefits. It also offers flexibility to adapt data models as requirements evolve, particularly when combined with CQRS. Despite its strengths, event sourcing isn't suitable for every scenario. For simple applications, small domains, or systems with little business logic, the added complexity isn't justified. If your system requires immediate consistency or rarely encounters conflicting updates, traditional CRUD may be more appropriate. Event sourcing is also less useful when real-time updates to data views are essential, or when the overhead of managing events outweighs the benefit. Always weigh the trade-offs before adopting this pattern. Consider a conference management system that tracks seat reservations. Traditionally, you might store the total number of bookings in a database and update it as reservations are made or canceled. However, this can cause scalability issues during peak times. With event sourcing, each booking or cancellation is recorded as an event. The system calculates available seats by replaying these events. This approach not only scales better but also provides a complete audit trail of all bookings and cancellations, making it easy to restore state or analyze trends. Let's walk through the booking workflow. When a user requests to reserve seats, the UI sends a command to a handler. The handler reconstructs the current seat availability by replaying booking and cancellation events. It then processes the reservation, raises a new event, and appends it to the event store. If a seat is canceled, a similar process occurs, generating a cancellation event. This method ensures every change is tracked and the system can always restore the exact state at any point in time. It also supports scalability and auditability, even under heavy load. Designing with event sourcing, consider how it supports reliability and performance. Capturing a full history of changes helps with disaster recovery and state reconstruction. Combining event sourcing with CQRS and strategic snapshotting can optimize performance by reducing the need to replay long event streams. However, always balance these benefits against the added complexity and ensure your design aligns with your system's goals and requirements. Event sourcing often works alongside other architectural patterns. The CQRS pattern separates read and write operations for better scalability. The materialized view pattern creates efficient queryable views from event data. Compensating transactions allow you to reverse changes by adding new events, rather than updating existing ones. As you explore event sourcing, consider how these related patterns can help you address your system's unique challenges and requirements.